Check it out now, y'all.
Nano Hub U, online instruction.
Welcome to module 2.4 of the second week. And just to remind you, what we discussed in the last module was we took our expression for conductivity that we had obtained actually last week and showed how you could connect it to the standard Drude formula, the one that you learn in freshman physics, the one that most of us kind of carry in our head and the one that usually shapes our thinking, namely that sigma is equal to q squared tau over m times the density of electrons, that is number of electrons per unit length if it's one dimension, per unit area if it's two dimensions, per unit volume if it's three dimensions. So this is the formula that you kind of carry in your head, and often people take the conductivity and divide it by the carrier density, this electron density, and then the quantity you get, that's what you usually call the mobility. And with any conductor, when you perform experiments, one of the quantities you try to measure is this mobility, which is conductivity divided by the electron density. And of course, the implication is that ordinarily conductivity should be proportional to the number of electrons, or this electron density. And what I want to point out here is that, well, if you did not have a parabolic relation, and a good example of that is, say, graphene, where energy momentum relation is linear rather than parabolic, E is proportional to P rather than P square, and in solids in general, you could have more complicated energy momentum relations. Okay. But the point is, if it was not parabolic, then you see this mass should be used with caution in the sense that the mass actually is not a constant. And in graphene especially, as we'll see, the mass keeps increasing as you go up in energy. What that means is that if you did an experiment where you gradually change this electrochemical potential, so at first you are here and you have a certain number of electrons, and you keep raising it, and as you raise it, you have more and more electrons. And you might think, well, if I now take the conductivity and divide it by the electron density, that should give me the mobility. Well, what you'd find is that as you raise your electrochemical potential, the mobility would just keep going down. Why? Well, not because the mean free time is getting any shorter or anything necessarily, because usually when mobility goes down, you figure, well, maybe the electrons with that energy have a shorter mean free time. But the point is, in a situation like this, the mobility could be going down simply because the mass is increasing. So it is as if when you fill it up and you have more electrons, so the electrons up here are much heavier, quote unquote, than the electrons down here. So it is as if just the mass increased. And all experiments show that indeed when you measure mobility versus electron density for graphene, the mobility does go down in a way that you'd expect, really, just from the fact that the mass is increasing. So this is an example of a case where, you see, this simple picture we carry in our head needs to be qualified. Otherwise, a lot of well-established results can look pretty puzzling. Okay. So the main thing I'd like to show you is, for example, in graphene, actually, instead of conductivity being proportional to electron density, we'd actually expect it to be proportional to the square root of the electron density. And let me explain how we get that. So the way we do it is, you see, what we had done in the last module, if you remember, we started from our expression. And the point I made in the last module, I want to repeat again, that this expression of conductivity in terms of the density of states and the diffusion coefficient, that really is the general one that one should normally use. The Drude formula is really an approximation that sometimes works, but if they don't agree, or if you don't quite know what to use for mass or how to use it, the formula one should fall back on is the one that we obtained last week. Really, that's this one. So what I showed in the last module was how this could be rewritten in this form, provided mass was equal to, this was defined as P over V. And this also again is worth noting, because in the literature when people talk about effective mass, there are various ways in which they define it. And this is not necessarily the only one you'll see. You'll see some expressions which look like 1 over m is equal to dV dP, or which is like second derivative of E with respect to P. This is actually what you'll see as the definition of mass in many textbooks. But the point I want to make is that in the problems we are discussing, if you want to get consistent results, you really should view mass as P over V and not any other definition, really. Now, what I want to show is, next, is that from here, once we take into account the fact that the mass itself is kind of energy dependent, you'll find that the conductivity, instead of being proportional to n, will actually become proportional to square root of n. So that's what we'll be doing. And what that graph up there shows is what you get if you plot the conductivity as a function of electron density for graphene using these numbers. And there's been many experiments, and I cite one of them here, which you can compare to, just to show that, experimentally also this is just the kind of thing you normally see. Okay. Now, so what I want to explain then is how we get an expression for conductivity that is proportional to the square root. So earlier we had obtained an expression for this n as a function of P for 1, 2, and 3 dimensions. We are now talking about graphene, which is a two-dimensional conductor. As I had mentioned before, basically what it consists of is one layer, one thin monolayer from the surface of graphite. That is, graphite, as you know, is a well-known solid where these different layers are very weakly coupled to each other, so they peel off easily one from the other. And one of the major developments of the last decade was that people were able to actually peel off essentially a monolayer from the surface and make measurements on it. And that's what is usually referred to as the graphene. That's this one monolayer of carbon atoms arranged in a hexagonal lattice. And in graphene, it's believed that around the chemical potential, the energy momentum relation has this linear form. Now, since we are dealing with a two-dimensional conductor, then I'll use just the two-dimensional version of this, which is, we put a d is equal to 2, and we use the second one here, the pi WL. Now, the expression for conductivity that we already have, looks like Q squared tau times V over P. That's what is written there as 1 over mass, and then N over W. Now, if the energy momentum relation looks like this, then you can see that the velocity, which is defined as derivative of E with respect to momentum, that's just a constant, V0. And this is, of course, very different from the usual parabolic relation where velocity is proportional to momentum, is P over m, of course. But here it is a constant. So we could write here V0, that's velocity. Now the question is, what about P? Well, we could use this relation to relate P back to N. So that way, we can eliminate the P from here and we'd have an expression for conductivity in terms of N alone. And so, the way that would go then is, from here, I can write P over H is equal to N over pi WL square root. So all I did is P over H squared is N divided by pi WL, and then I take square root on both sides, so that's it. So instead of this P here then, so I could take off the P from here and instead replace it with what I have from here, right? So you'd have this is like 1 over P, so I'll write this here as is equal to H times that's it. So instead of the P, I have put in what I obtained from that relationship. That's it. So I can take this off from here. So now if I simplify this a little bit, I think you'll get Q squared over H. See, that's the quantum of conductance as you may recognize from week 1. Square over H. That is this V0 tau. And you'll notice there is N, there's this electrons per unit area, but then there's a square root of electrons per unit area. So you get square root of pi times, let's write this. Yeah, I think I got all the factors. So that is basically it. So sigma is proportional to the square root of electron density rather than the directly proportional to electron density. And, and the quantity that is appearing here is like the mean free path. It's like mean free time times the velocity. Again, as you know, there is this factor that you have to insert. It is some number of the order of 1 times the mean free path. Yeah. But this would then be the expression for conductivity in graphene. It won't be proportional to N. You would actually expect it to be proportional to square root of N. And that's the plot you see up there, actually. You'll see these, and there's 2 plots, one corresponding to a particular choice of the mean free path, and the other corresponding to a different choice of the mean free path out there.